Right, ladies, let's take a look at the rest of diffraction. So, in the previous video, you saw that water waves can undergo diffraction. So now, if light can be diffracted as well, diffraction can be used to prove that light has a wave nature. So, the first thing that we can look at is activity 6.1 on page 127. And this is something that you can go try at home if you really want to. So you can see the setup that they've got over there. So we've got a black screen at the back, and all of this should be on a dark surface as well. We've got a source of light over there. Then they say you should use a cork and put your needle in a piece of cork, but you can use anything, I'm sure. Over here, we've got a piece of wax paper, and then this is where you're supposed to sit and look at the needle when the light is on. If you don't want to do this, then you can also just go try this. They also say you can hold a needle at arm's length to a light in an otherwise darkened room. So you can use a torch or something like that. Observe the needle through a narrow slit in your eyelids. So one eye should be totally closed and the other one should be almost closed, and then you look at the needle. Now, I don't think it's going to be as clear as this picture, but this is the idea. This is what you should see. So you see these light and dark lines on around the needle, which actually shows the diffraction of light as it bends around the edges of the needle. Now, the next thing we will definitely do once we are back at school, but this is the idea. Over here we have a source of light, and here we have got a single slit, a tiny opening over here, and here we've got a screen. So the idea is that the light will shine through this slit, and then some sort of pattern will be observed on the screen over here. So the first part of the experiment, our source of light is normal white light, and then the pattern on the screen looks like this. So we see that in the middle we've got a broad central band of white light, and very important, this band of white light is much wider than the slit. So if we go back over here, this will appear over here on the screen, but much broader than the actual width of the slit that we've got over there. But we don't just see the white light over here, we see that the pattern is more spread out on the screen, and we have got that the white band is flanked on either side by dark bands, and then as well as bands of spectral colors, in other words, all the different colors of the spectrum. And the red is always furthest away from the center. So yeah, the red is over here, then black, and then the red is over there. Then if we go back here and we replace our source of light with a red light, and here we talk about monochromatic light because it's light of one color only, it's only red light. The pattern on the screen then looks like this. So I've got a central band of red light, and on either side I've got a black band, and then red again, black, red, and the same on that side. And this central red band is much broader than our previous white band over there. And then lastly, if I replace the red light with blue light, once again this is monochromatic blue light because it's only blue light. The pattern then looks like this. So the central band over here, blue, and then black bands on either side, blue again, black, and so on. And although similar to the red light, all the bands are much narrower compared to the red light. Then to explain this, we've learned previously that there are two factors that influence the amount of diffraction, and one of them was wavelength. And we also learned that degree of diffraction is directly proportional to wavelength. And that is the reason why The red light, because it has the longest wavelength of the different colors of the spectrum, it is diffracted the most, so you'll see the broadest pattern there, compared to violet or blue or green, and those colors have a shorter wavelength compared to red light, so they will undergo less diffraction and a narrower pattern will be seen on the screen. Okay, now our second factor that influences the amount of diffraction is the width of the slit. So over here, I've got red light, of course, in both cases, but over here, I've got a broader slit compared to over there. So with a broader slit, we can see narrower bands, so there's less diffraction. And with the narrow slit, we've got more diffraction. And this should also make sense because we have already said that the degree of diffraction also depends on the width of the slit, and that degree of diffraction is inversely proportional to the width of the slit, and that is why a broader slit will have less diffraction and a narrower slit will have more diffraction. Then just to explain the bands, why do we see if it's red light, a red band, and then dark, and then red, and so on? And this is because of interference. So where you see the color, like over here, this is as a result of constructive interference. And where you see the dark band, that is as a result of destructive interference. So here I've got constructive interference again, destructive, constructive, and so on. And then maybe, just to explain that a little bit more, if we take a look at this diagram over here, now this was the answer for your homework question as well. Now imagine that over here we've got our source of light, we've got our screen, there's the opening. The light waves also bend around corners and you see exactly the same pattern. If I place a screen, let's say over here, on the screen over here, let's just move that down, we will have the colored band. So over here, constructive interference takes place. So I've got the red band, for example. Here I've got destructive interference, destructive interference. So the red band is in the middle, if it was red light that I used. And on either side, I'll have a dark band and a dark band. And yeah, there would be some more constructive interference, and on this side as well. So red band on either side, dark band, and then red, and so on. So that actually shows how interference causes the different colors that we see. So just to finish off, diffraction, this is a wave phenomenon, and the fact that we can clearly see here that light can undergo diffraction proves to us that light has a wave nature. So we can actually say that because light undergoes diffraction, it proves to us the wave nature of light. And then lastly, because this is the end of the section, chapter 6 revision questions you'll find on page 130. There are some exam practice questions, topic 3 as well, on page 133 and 134. So we'll do the same as before. The answers to these questions over here, I will post on Friday. These questions you can do in your own time. And once we're back at school, when we do a revision, we'll take a look at those answers. And the reason why I'm only going to post the answers for this on Friday is because I know that you're also busy with that test that Mrs. Maharaj has posted for you. So on Friday, I'll post the answers. And on Monday, we can then get started with the next section, which is going to be a chemistry section. And we are going to learn all about gases. Thank you very much, ladies.